this is exam 3, part 1, and we're asked to write down a set of Crank-Nicholson finite difference equations, paying special attention towards explaining how you arrive at the finite difference equation for the insulated boundary. And first thing we need to do is state the Crank-Nicholson equation, and it goes as temperature at current position J at the next time, so n plus 1, minus the temperature at current position n and current time all over delta t is equal to thermal diffusivity, thermal alpha over 2 times dx squared times temperature at the next position J minus 1 at current time minus 2 times temperature at current position n time plus t at the previous position current time plus temperature at the next position, so J plus 1 at the next time minus 2 times this is basically this over here, but at the next time, so temperature at the current position at the next time plus this, which is temperature at previous position at the next time. Okay, all right. And so what we want to do is take the average of the second order finite differential equation at the next time and current time as well. So we need to split these two, this temperature at the current time and temperature at the next time. And to do that, the first thing we're gonna do is distribute this delta t over here, and what this gives us is simply alpha times delta t over 2 times delta x squared, and we're just, for simplicity of things, we're gonna call this value r. Okay, and so when we rewrite this this whole equation on top, we get something like this is equal to r times all of this, so tj plus 1 and minus 2t j to the power of n tj minus 1 to the power of n plus tj plus 1 n to the power n plus 1 minus 2t j n plus 1 plus t j minus 1 to the power of n. Close that. So what we're really trying to find is the temperature at the next time, n plus 1. So when we do that, we're gonna bring all the variables with t to the power of n plus 1 on one side, and all the values with current time on the other side. So we're just gonna have to distribute the r into here first, and when we do that, we get this tj n plus 1, okay, minus, okay, this comes over to the left and gets a negative sign, so r times this times this, that n plus 1, okay, so that's plus, becomes minus RT J plus 1 N plus 1 plus, okay, so that's minus 2R. When you bring it here, it becomes plus, so plus 2R TJ N plus 1, and then minus R, okay, this plus becomes negative. This is N plus 1, I forgot it over there, okay, so minus R TJ minus 1 to the power of N plus 1, right? Yeah. Okay, is equal to, now we do the TJs to the T to the power of N is equal to, okay, this so plus TJN, okay, and we're gonna have R TJ plus 1 to the power of N, so plus R TJ plus 1 to the power of N, and then we're gonna have minus 2 R minus 2R TJ to the power of N, and then we're gonna add plus that RTJ minus 1 to the power of N. Okay, that's just basic algebra. And then we're gonna combine like terms. Okay, so when we do that, we see that we're gonna combine this, the TJ plus 1s, okay, and we're gonna combine the TJs. We're gonna combine the TJs for this one, okay. And so when we do that, we get something like minus R TJ plus 1 and plus 1, okay. This stays the same. There was no like terms. This stays the same and this stays the same, okay. And then we're gonna add plus this 2R, okay, TJN plus 1, and this TJN plus 1 becomes plus 1 plus 2R TJN plus 1, okay. And then when we move on, we get minus, okay, that RTJ minus 1 and plus 1, yep. And then we're gonna get that equals to, come here on this side, combine like terms, the TJs are the same, so that gives us RTJ plus 1 to the power of N, this value over here, plus we get 1 minus 2R TJ to the power of N, okay, and then we add that plus RT to the power of N J minus 1, okay, and that is the equation that we're looking at. Alright, and so now what we want to do is put this into a matrix, and so we're gonna start by creating, so we're gonna call this first set of values coefficients, and our coefficients are gonna go as 1 plus 2R, okay, and then we're gonna have minus R, and we're gonna have minus R, and then we're gonna have 1 plus R, and the minus R, and then we'll have a minus R here, and the rest is just zeros. Okay, so it's zeros the rest of the way, which when we do this, we get R, we do this, we get something like 1 plus 2R, and then this we get go. Okay, and then minus r, and then the next thing. So these are coefficients. The next thing, we're gonna multiply that by our knowns. So the tj n plus 1. Okay, which the question asks to do from 0 to 50. So we're gonna have our first one is t0, and we're gonna have our second one, so t1 and plus 1, keep going until we get to t49. Okay, and then this is gonna equal to r. Okay, so it's basically this for the first one. So t0, we're gonna get r t0 to the power of n plus 1 minus 2r t0 to the power of n plus r t. So previous, it's not even j minus 1. Okay, and then we go on, we'll do the second value. So t1, that becomes our t j plus 1 plus 1 minus 2r tj, so 1 and plus r t0 j minus 1, so the previous one, and we keep going until we get to the last one. And that this is basically the left side, and the far right temperature. Okay, temperature right, it says in the question that it is insulated. Okay, and what that means is that the temperature at 50 is the same. If it's insulated, it's the same as the one previous to that. So the one next to it, so the tj is going to be the same as tj plus 1. So when we come and look at our equation over here, we see that what happens here is our tj and our tj plus 1 are all the same. They're the same. So what will happen is this r is going to come and get added to this, which makes it 1 plus r. So this side becomes 1 plus r. Okay, and on this side, same thing happens, where our r tj plus 1 and our tj 1 minus 2r tj to the end, they're both, these values are the same. So this r comes and adds itself on here, making it just 1 minus r. So when we write out the equation for our final temperature, it's going to be r, okay, tj plus 1, okay, to the n plus 1 minus r, instead of 1 minus 2r, tj to the n plus r t to the n j minus 1. Okay, all right, and that should be it. Thank you.